Perfect. Okay, so we are now live. Yeah, so Sagi's going to talk about work he's been doing on 1D EM inversions. And then we can pull up any pull requests. There's stuff to go over there.
Spectral IP is in.
It is.
Yeah. Same.
Congrats. That was a
Took a long
congrats
time.
to you too. Wow.
That was a big one.
Yeah.
I put a small pull request on to just lighten up a little bit of the stuff on the mass matrices, so I'd appreciate your input.
Oh yeah.
But
I mean, that was way bigger. I think the scope was way bigger.
it is huge.
It's like a spectral IP was like it's small.
Yeah.
I've used your PR to push new stuff too. To be honest with you. Yeah, this is an update.
There's a lot of stuff.
But I think that actually PR is pretty good, right? Like that,
Oh,
that
yeah.
sparse inversion is actually working
It's
well.
way better right now.
And
It's
we
very cool.
improved the efficiency of the EM code. So yeah, it's actually nice.
This is an excuse. It's an excuse for other stuff.
Okay. Okay, so I'm. It's been some time, like actually a couple of months. I think when we started working on 1D code. The idea is like we got all the 3D codes, but we don't really have one. We have a 1D code, but there's some missing points in our 1D code. So I think I want to compensate what we don't have. And like the basic idea is actually like doing all the 1D, but when you're inverting it, you want to constrain laterally. So that's a basic idea, but there are quite a bit of details inside. So frequency domain is kind of a bit easier because you just need to, you just get data and invert it. That's probably it. Processing part, I'm not sure how important that is, but time domain, there are quite a bit of details. So sometimes you need to know, let's say you got a transmitter here, and I didn't put a receiver, but let's assume there's a receiver over there. And not only just Earth, receiver itself has a response. And then you need to take account sometimes. So those are the details. And the waveforms can be fairly complicated. And the altitude, you don't really know exact altitude. Let's say you got a tree here, then you used like a kind of radar. Mm-hmm. Then you don't know which one is true height. So that's the details, and your sampling rate is much higher than your measured time channels. So they do an integration for their time gates. And also, at the end of the day, you want to invert that in a spatially constrained inversion. So those are the kind of missing pieces in our code.
I always wondered why they need to do the elevation correction, because usually radar is good enough, right? But I guess vegetation makes a lot of sense.
Right. That's one reason, I think.
Yeah, but there are tools to filter the vegetation out of the laser and radar altimeters. So usually that will be part of the database. You given like probably like the raw and the processed elevation, but it's kind of like a low pass, like a low pass filter. Like the trees usually show like kind of like very high, like a sharp spikes, so like you kind of like remove that with a low pass filter.
But it makes sense to do it with the transmitter too, yeah.
Right. And then I think there are probably could be the other reasons why the altitude could be wrong.
Yeah, I guess also like if your radar is on the bird and the bird has a very like a high inclination in some direction, that might affect also your altitude.
Right. Yeah. So those are the details, and when we're inverting, let's say specifically for time domain data, we need to take account that sometimes or not. But it's very important to check whether that effect is very important or not, because if you did not consider that, and like guys like Skype and people may come and, oh, did you consider that? Mm-hmm. And then we didn't, and then they say, oh no, then the result is not very confident. So it's good to have that capability at least, like check whether that is important for our case study or not. So that was a sort of goal, and I didn't mention that waveform, like we usually consider a single pulse, but it's actually multiple pulse, and then we stack it. So that effect could be important, depends upon the case. So let's so that was the idea, and yeah, so I wanted to consider all of those, and at least in the 1D code. So that was most of the development. So for instance, show you how the receiver response could look like. So those are, the black one here is the step off response. And then you can consider the receiver response as like a kind of low pass filter. So if you kind of change the frequency, then as you go lower frequency, that's the blue. So that like a receiver response can have an effect on, especially at the LV time. So if you know that, if you can put that, you may want to put that in. So at least SkyTem system actually provides that low pass filter, so we can put that information in if you want.
When you're saying you put that in, do you put that in like as a part of the receiver? Like, is it implemented as a
no, here I didn't actually use the sources in the receiver class. I just used a survey. Okay. I could show you a look at that later. Yeah, so this problem doesn't, like, it's very different from our typical PDE code. So the structure might be different. Yeah, I could comment some of the details. There were quite a bit of unnecessary part.
Yeah.
Anyway, so
actually, in most of the time domain conversions that we've done at the early times, we do tend to be under fit. Right? We're always a little bit. We're always a little bit low.
Mm-hmm.
So it might be that a lot of, and crosses different systems too. I mean, it's just sort of one of those general things, whether it's V10 data or SkyTem or anything. You know, you fit the curve, and then it's just really hard to fit those early times, and we're always biased under.
And I'm sure, like, if the coil heats up, I'm sure this changes constantly too, right? Yeah. After, so if you don't account for it, is it going to be like a conductor on your surface conductor? Like you're gonna
right. Yeah, you put I think that kind of depends, right? Like it's DBDT data, so your slope can be like, you can have larger response at the LV time. So that I think that depends, I guess. You could either put a conductor or resistor, depends upon which regime you are in. Remember that the DBDT curve, it's not like always increasing when conductivity increases. There's a crossover.
That's true.
So B data, like a magnetic field, actually increases as conductivity increases.
Okay.
So yeah, anyway, like a near surface will be distorted because of that.
Yeah.
Okay. So that's an effect. So I actually put that in. So the little bit of detail I'm doing that in the frequency domain. So I generate the low pass filter in the frequency domain, multiply that, and then use that to transform to time domain. So that's actually kind of annoying when we're solving PDE code, like if you're solving directly in time.
Yeah. The convolution.
Right. So I think in theory we can put that into a waveform because that's a linear response, but you may need very fine discretization. I'm not quite sure how we could test, but that's a kind of annoying thing. So yeah, so I think that's one thing. The other thing.
Excuse me, why do you think that would be so hard? I mean,
No, there's nothing really hard, but if you think about our time stepping, it's very sparse, right? So, well, like we can convolute, no problem. Like doing it, actually, there's no problem.
Yeah,
but
okay.
If you want to convolve it, then I don't know. That depends upon, okay, are you going to do linear sampling? Then it's going to be like expensive, right? Especially for sensitivity computation, right? The response is kind of fine, but if you think about that, like when you're computing the sensitivity, then you need to convolve every cells.
Right, yeah.
So they're like it's a, yeah, there's nothing hard, but there's some sort of computation level. So that's the details that we need to know. So in terms of 3D, if you don't have to do it, that's great. So but if you really need to do, we need to think about what is the efficient way to actually incorporate that. That's a question. I'm not sure what is the real solution to that. Okay, the other one is the waveform. So first test is actually just a step off and ramp off. So this is a simple exponential function. The blue one is just true exponential function, and the orange one, if I put a ramp off. So it's actually pretty different. And for real EM response, that's hugely different, especially at the early time. So putting a right waveform is important. That's actually what we're doing, so that's fine. And the other one is the, let's say this one. So we have a two pulse, right? Meaning, we probably need better plots, I guess, to explain that. But you need to take account that stacking, right? So for a single pulse, you have one response. But for a double pulse, you have two responses. And for a response at the first pulse, kind of made an effect at the second pulse. So you need to take account that stacking. I think, John, I think you know what that means, right? Like a IP response, for instance, right? You have a first pulse, and then you have an off time. Yeah. Right? But that off time response may affect on the second pulse response, right?
Well, yeah. Once it's stacking, because it's literally just like a moving average filter of all of them, stacking them on top of each other, and then there's in the end result, it's going to affect it. Yeah.
Exactly. So especially when your decay is very slow, that effect may greater and greater. So let's say you're in a very conductive medium, then that effect could be pretty large, or not. So,
are you only stacking the two, or are you stacking a larger?
I'm just doing two here, but so that's what I meant. Sorry, I'm using the whiteboard. So the first response may look like this. The second response may. So when you're stacking, I think you have this response. So you need to take account of that when you're stacking. So you need to stack this, and minus that. So when you have a multiple, you can take account. So this example is not that big.
Sorry, did you guys have a question?
Oh, no, I was asking, maybe can you just model multiple pulses?
Yeah. That's what I'm doing. So this is the third, at the first line is the first pulse, and the second line is the double pulse. So it's not that big, but at late time there's some difference. And depending upon my conductivity structure, that may be different. Right? If I increase the conductivity, that discrepancy could be larger. So I think that's an important fact. Okay, I need to test whether that's a very important effect or a minor effect. Then I think we have something to say. Okay, that was pretty minor for our case.
But when a contractor gives you the data, aren't they supposed to level, to get rid of those shifts and just stack it, and then gives you just
Yeah, I think what we're getting, it's a stacked data.
Yeah.
So I think it accounts multiple pulses. They didn't correct that.
Okay.
I think sometimes they correct by doing deconvolution.
Okay.
But there's an argument whether doing that or actually putting all of that as a system parameter in your inversion code. There are some arguments, but that's what we're getting.
So the late time response would always decrease, or it could be bigger because you're shifting the phase wave from positive to negative. So you would expect the response at late to be.
I think that for like a coincident loop system where your response is always positive, I think then that'll decrease the late time response. Same thing happening is ramp on and off, right? So that actually changed the sign of your responses.
Mm-hmm.
So yeah, taking account that is important. Anyway, so that's a waveform. So here I'm just doing a 2-pulse, and it seems like doing a 2-pulse is usually enough for a given measured time for like everyone's system.
Where did you get that from?
That was in the reference. I could send. I'll share the paper today. And I'll send you.
I remember when this issue came out, the number of, well, many years ago, some of the groups in Australia claimed that, okay, at least for their system, okay, so they're in a conductive environment, right? Mm-hmm. And there they needed at least 3 or 4 to art rate, I think that's fine. Yeah, that's fine.
So, okay, I think that's a good point. And then I think, like for instance, let's say this is a simple exponential curve. And then I was using 0.002 for tau, time constant. But if I increase that tau to 0.01, your double pulse is like much less. So I think so the blue one is the double pulse and the black one is the single pulse. Okay. So yeah, depending upon how your time decay, that's different, right? If your like a response decays slowly, that'll always make an impact. So I think it's kind of like that comment is kind of like a bit tough. Right? That really depends on your system parameters and also the connectivity of your.
So in that sense, is it worse to stack more pulses because that effect's gonna not be fully cumulative, but it's gonna keep adding up and adding up, right? In theory, like let's say you had like a superconductive, so your response really drags a long time. As you keep stacking more and more, technically you're gonna start tapering all your signal.
Yeah. There's a trade-off, like that's a speed, right, for the warn.
Oh, right.
Like we have a certain speed that you need to move on. Of course. So that's a trade-off.
Okay.
So I'm not 100% sure how many stacks they usually do. We could compute, I guess, like because we know the speed and what is the spatial resolution. But anyway, so that's the waveform. And the other thing is the altitude. So I'm going to show you one example. So here I'm using the frequency domain system. That's actually how the code looks like. You need to put the frequency in. So here, it's like a resolve frequency. Then you have your RX location, 30 meter above the topography. And you can use the field type either secondary or private, like a total field, your RX type, source type. Your offset is 7 to 8 meter. You need to put the depth in. That's the spatial discretization. And you need to put the frequency into your survey. And here, I want to invert both conductivity and the height. So I'm using the wire map. So it's like kind of like a generating projection matrix for a model. So my model is not only a conductivity and also the height of my transmitter and receiver. So here, the transmitter and receiver are at the same height. So I'm just inverting for one. But depending upon the case, like, okay, we got a fixed wing system where you got a transmitter here and the receiver there, and both of them could be wrong. So you need to invert for both, which might be tough.
And are you using an analytic sensitivity or finite difference?
No, I'm using analytic sensitivity. So.
And for the edge for inverting for the height, are you using the height from the data as your reference height, or is that not really taken into account in the inversion?
So my initial is the reference. So I'm using the default SimPEG inversion setup. So I'm putting in some sort of initial. Yes.
What's your initial? Okay, so what's your initial?
Okay.
Yeah, what's your initial and reference edge?
Yeah.
Okay, I'm getting
That's a
that.
good question.
So I'm putting the M true, and then that's M true DH. So let's say I'm just putting the so M true is the true, like a true height.
Yeah.
with the same model, and then true DH is the same model, but the height is 5 meters above.
Oh, that's a lot.
Okay.
So why did you say you had to worry about two height differences?
Okay. So for like a resolved system, we have a kind of rigid system where we got a loop or something like that, right? So in that case, we have a helicopter here. Right? So in that case, we don't really need to worry about too much about this height from the transmitter and the receiver. It's basically the same. Right? There probably have some sort of tilting, but let's assume that's pretty minor. Okay. So for like a VTEM system or a SkyTEM system, which you use actually co-located loop, that's still fine. Got a loop like this, and then that's a TX and RX. Right. So it's still fine. But let's say we have a fixed point system, now we got a plane. And the receiver is attached to here. Then, yeah. Okay.
I get two.
So we got two. So both of them could be wrong. So here, in the code, I'm assuming I got pretty good Z minus H. So I'm just inverting for H, assuming that in the code. But
that's kind of where I was thinking, because you generally know the distance between your source and your receiver, right? So if they're both wrong by the same amount, doesn't make any difference. So you really only have one height.
Yeah. So when
But they do compensate for that when they serve. I mean, this is not like 100% thing. Because if they change your speed, then the angle of your wire changes and then the elevation changes. So they compensate technically in the field, but it's a calculation. It's not a given.
Yeah. But I guess in practice, there's a question of whether it would matter very much if your source, which is way above, is is changing a meter or two. Compare, because that's just then changing how you're influencing the Earth.
Right.
But that's the main thing is where your receiver is with respect to the Earth.
Yeah, that's a good point. Yeah. So
Anyway,
that's sort of like a scope here, and I'm doing a simple thing here. And actually, so this is like a finite difference sensitivity. So I'm just testing whether my analytic sensitivity actually matches with the finite difference sensitivity. So it's like for this one, still doing a finite difference is cheap, but analytic is cheaper. So analytic is one solve of predict like a 4 problem.
Yeah.
But the finite difference at least 2 solve.
Yeah.
So
nice.
so if you could do an analytic, like you would do. That's the data. So with this 5 meter, you got pretty high, pretty big difference. And that actually depends upon the conductivity of the Earth. So if the Earth is very conductive, that difference is bigger. So that you may have a better chance to actually kind of recover that true height. I think what was it? My conductivity was 0.1. Actually, and then I got I think I'll show you later. But so you can. That's the inversion code. So if you look at my input, M naught is half space conductivity. I got a conductor as well. And then I'm putting 35, which is wrong height, as my initial. Okay. Now I'm running the inversion.
How are you regularizing? Are you regularizing the height independent, or are you just?
That's a good question.
Or is it being included in gradients?
No, actually that's a good question. I didn't. I'm not. Actually, I'm regularizing. Putting alpha S1. That's a good point. I think I could actually just put 0. So I'm not regularizing now.
Okay. But before you were regularizing just with a small instrument?
Yeah, I think that.
Oh, sparse.
Going to do that. So. But that regularization, it's just one parameter, so I'm not sure. Like a gradient term doesn't do anything.
That's probably why it's crashing, because your gradient term is probably nothing.
Right. So my true was 35, recovered is 30.7, so that's pretty good. And the recovered model looks like this.
Nice.
So that's not too bad. So you can actually invert for both. Or you could do just a half-space inversion, for instance, like just inverting for half-space conductivity and the height.
Yeah.
For instance. So this is the same example, but here I'm inverting for a half-space conductivity and the height. Then I started from 50. Then actually I got the 30.5, and that was the true conductivity. And then that's what I recorded. So I think that's not too bad.
You have to balance it, because I mean, can't you just like change the height to get the, since it's a single conductivity value you're inverting for, it could be, you could like play on each at the same time. So
that's what I thought.
How come you ended up in the right place?
That's what I thought, but it seems like I don't really need to. When you actually got the sensitivity. So frequency domain there was actually working pretty well. Because if you think about, we got pretty high frequency. We got 100K for the highest frequency. So that was good. But for time domain, I couldn't just do inverting them together. So we may need to wait. So I think it's less sensitive. So when you actually got the sensitivity, then I think putting them in and inverting together without even waiting, I think that was pretty good. But for time domain, I had to just inverting for half space and the height. Otherwise, it didn't really work well. There are probably some sort of waiting.
So how is your fly height?
Pardon me, the one?
How flexible? Like plus minus 3 meters, or do you have like some sort of restriction or like the constraints for the?
We could put that in. So we could put some bounds constraint. Here I didn't put.
Okay.
But yeah, it was. I think so. Here this example I started from 50, and then the recovery was 30. So seems like okay.
Okay.
But depend. I think if you don't have like a really good sensitivity, then it can fluctuate a lot. Yeah. So in that case, you may want to put some sort of like a bounds in.
Okay.
Or put a regularizer on your edge with a laser as a reference.
Right.
Edge frame.
Here, I think I'm doing that. Here.
Okay.
So that initial was my reference model. So I think that's what alpha S does, I think. So that alpha S1 meaning I had a reference model that I got something. I got it from somewhere. Okay, so I think that was about it. So that's all that's considering all the different effects. Time gate, I haven't tried, but there are some ways that you can actually kind of just correct that. I think I haven't tried that yet. Okay, then I'll just show you one more example. Right. Yeah, I think I have shown this before. So that's a frequency domain example. You could do smooth and L2 inversion. But I have a little bit more exciting example, Bookie.
Bookie.
Here's Bookie Dequan.
Oh yeah, it shows up again.
Yeah, it's a test example. So this is a Brook-Purnong example. So here we have Murray river at like it's somewhere in Australia. And that's the data. So here, now we're doing like a laterally constrained inversion. So that's actually basically kind of very similar to what GeoSci.xyz does. So like they have each sounding has the same number of layers. And then for each layer, we're putting some sort of like a smooth constraint in the inversion. But here we're putting all of them together at least. So we got one objective function. So we're minimizing that one objective function, which is nice. And then we're asking in like for each node, we want to have some sort of smooth model.
Okay.
Okay.
Can we go back to your mesh or like neighbor thing? Like seems that just on the side, like seems a bit thicker. Is that because you actually like for the side you are actually like you fetching neighbors that are further away?
Yeah. It's going on, right? So it's gonna, if you don't limit the distance, then it's gonna connect as many points as possible.
Okay, because basically what you put as a constraint here is how many neighbors. It shows that. Or?
No, I think we just put for each node, like for a single node, we have a number of like a neighbor, right? Yeah. So I think that's the constraint. So we're putting just +1 and -1 for each of connections.
Yeah, but I mean for a single node, you say like you connect to that many neighbors, or do you choose this number? Or?
No,
we don't choose.
So it's just yeah.
Okay.
Yeah. So I think for this one, I think we got 6.
Okay.
6 connections, right? I think that's what we're doing.
Yeah. Okay. I was just trying to understand why you have like this very like thicker portion that seems like you're connecting like points that are like all along the thing.
Yeah.
It's because your lines are close to each other and it looks like it's thicker. That's all.
Okay.
Yeah. Good. Then you run the inversion. Actually, this one takes so it's about 1,000 sounding. I got 5 frequency. So it actually takes about 6 minutes. So that's actually pretty good. So that was in my workstation. I used the 6 cores. And then if you have more cores, actually that'll be faster. So the efficiency is not too bad for a frequency domain. Right. So that's the model. How the model looks like. And I actually tried just to test. So here, so this one, I'm not actually putting any like a spatial constraint, like horizontal constraint. I'm just asking for a smooth model in vertical direction here. Mm-hmm. So yeah, like looks okay. But now let's say, okay, but I want to have a smooth solution in the horizontal direction, and that's how it looks like. So if I go back and forth.
Yeah, it's smoother. Yeah.
So is that, sorry, the second one is constrained in one dimension or in both?
So X is not X is more like a radial direction, right? We got a node, each node has some connection.
Right, but you're not doing just a long line here. This is actually
right. Yeah. Cool.
So your regularization is implemented on the triangulated mesh. Is that right?
Yeah.
Okay.
Then also you can ask for a sparse solution as what Dom developed. So you can actually have a sparse solution, right? Like you are asking for a simple model, and the model is simpler. That's done. I actually just got.
Is there any reason why you increase alpha X be 10 when you?
Oh, yeah, that was just a test. Like,
okay.
I want to have a really smooth model in the horizontal direction. So I may use 1 usually, but here I was like testing. Okay, here's my expectation, and is that outputs.
So it wasn't connected with the fact that you were then you're trying to do something sparse, or?
Well, I think it's still like a.
Oh, okay.
Still sparse. Right?
Yeah, no, I missed it. Good.
So Sogi, are you getting the same date misfit if you're having more smooth model?
Yeah. So all of them are reaching to the target misfit. I think they might be slightly different, but pretty similar.
Okay, I see.
Yeah, it's chi factor 1.
That's good.
Based upon the given data misfit, like a certainty.
And so I wonder if that L0, the bottom of that, corresponds to basically the depth of investigation that we're seeing. Could be. Yeah, so I think doing a sparse inversion for ground, especially for 1D inversion, like at the steps of 1D inversion, if you got a really right reference model, that gives you a pretty nice, a sharp boundary. And then below that, you may not be very sensitive like this. So I think that's good to have. At least showing 2 images of smooth and L0 inversion gives you a pretty good idea. At least a lower end, a top and bottom boundaries of this conductor. So that's I thought that's pretty good.
What was your ref here?
I think it was half space.
What about you remember that?
Can't go back.
And then minus 1.6.
Yeah. That's what I was
It's
thinking.
kind of close.
Yeah, 15 millimeter.
That's 1.
Plus, it's log, not log 10. Is probably what you.
Oh, it's log. Oh,
Is that right, Sag? Did you call it log 10 or just log?
I
That's
think it's
right.
log 10. Log 10, minus 1.6.
Right, but so you've computed sigma and then taken the log. You're not just plotting in.
Yeah.
Okay.
It's a log 10 sigma, not a log sigma.
Okay.
Okay. And actually, I just ran yesterday, so this is the that's a bit bigger data set. So that's a geotem data at
You did.
yeah. So actually, this is the phi Dussel. So phi Dussel is a time so what that means. So that blue to yellow. So flight is moving from blue to yellow. So that's a time. So, because it doesn't really matter for SkyTeam system, right? You know where the receiver locations are, and then source and receiver locations are same. But for a kind of fixed wing system, you don't you may know the source location, but you don't really know the receiver location. So then a flight direction is important. Which way are you going? Yeah. So
oh, nice.
so can I get that? And then what's interesting, it's not always just a same line. Because it's a pretty big survey, and then they stop sometimes. Oh, okay, look at that. Right.
Yeah, I told you that was gonna happen.
Right. But what's a good thing, they usually kind of classify that as a different line. So in a single line index, I think it's always increasing. So that's a good. So as long as we got that information, we can figure out which direction it was. So actually, I kind of take it account. And assign the corresponding receiver location. For 1D, that doesn't really matter. But still, okay, we got a sounding of depth profile. Where are you going to define that, right? So I would define between the transmitter and receiver, right? Yeah. Not a transmitter location. And that, it's 120 meters, so it could be really big. So.
That's a good question. What is it? What is the right answer?
I don't know. And that's the Delaney triangulation.
That's the red.
So that's the regularization.
What's in red?
That's where we got the DC line.
Okay.
And that's the inversion result. So that's the 5th layer. So if I can go up, change. So here they're looking for a resistor. And then I think this one is actually a good one. So that reds, those are the kind of their sand formation that they are interested, I think. And if you look at the section view, that looks like that. So
30K by 30K inversion. That's pretty good, man.
Yeah, so I downset the log for this case. I think it was about 2,000 sounding. I think it takes a few hours. So it's not great, but it's okay. But for this is my machine, so if I run it 6 cores, it'll take less than an hour. So yeah, it's not too bad. So if you got a cluster, it can be faster. And yeah, like you can make this type of plot. So I'll make that as an IO so that once you've done that, you can actually plot at least like a plan view and the section view so that you can. So those are the resistor, right? Like look at those guys. I think that's what they're looking for. And they got the ground EM data, DC data. So actually inverted, all of them.
Yeah.
And I think they were matching. So it's actually nice. So all done in SimPEG. So it's, okay. Anyway, I think that's it.
That's really exciting.
Yeah, that's beautiful.
That's cool.
Nice.
Do we give him 2 thumbs up or 2 stars? No, I don't know.
I like the stars.
The stars?
Yeah.
Okay.
I like the gold stars.
Gold stars.
That's my go-to.
That's right. Let's try.
That's great, Soggy. That's
Yeah.
really good.
Yeah. Taking it to the next level.
Yeah, and so the code is in
It's
SimPEG
in,
organization.
yeah, it's in SimPEG below SimPEG EM1D.
Cool.
It's not very well organized. Actually could,
Yeah, but it's nice to just know where it is so you can take a look and start getting.
yeah, probably good to have some of you guys, your inputs, because it's not. So yeah, I don't really like use a source class and receiver class.
Yeah.
I found, yeah, I found like probably it could be useful. I haven't figured out like what's a good way to do that.
Well, and this I think is actually perfect timing because getting the simulation class right, like the simulation class should work for this, and we don't want to impose assumptions that like are really baked into the PDE side of things that
Yeah.
you just don't need. And we sort of saw the same thing with Dieter's code as well. Is that well, I mean, first of all, that brought to light like the pairing of the survey and the problem was just completely unnecessary. But same thing is like working with the source type rather than actually creating a source object.
Yeah. That's good. That's good. One thing I didn't comment about that. So time domain code now, what it does, it takes like each data or each sounding location. You could put different waveforms or different sources.
Yeah.
So that means actually you can invert both like a nanotem and like a ground EM data and the airborne EM data together. So that's actually nice because like a ground EM data may have higher resolution, especially for the near surface compared to the airborne EM. So then like if you're inverting together using like a spatial constraint, you can actually get better resolution for airborne EM data as well. So I think that type of stuff is possible.
You need to use some kind of weighting on that data though, because they've got different sensitivity.
No, actually, no, I didn't have to. Here's a test. So the test example was, so I was motivated by actually that data set because I got a nanotem data that recovers the resistor really nicely. The DC and the nanotem matches really well. But I can recover resistor from geotem, but the resolution is not that great. So that all this time for geotem is about 1e-4 second, which is not that all the time. So this is my like a 1D model. Then I put just an nanotem here, and all of them are geotem. So I invert it together. So look at here, got pretty high resolution. You're resolving the resistor pretty well. Then it kind of gets worse, but I think it still helps by putting some sort of smoothness constraint in the nanotem data. And that's the sparse inversion. It gets better. So actually, we're putting the same model, but putting a constraint of the nanotem actually helps to better image this resistor in the geotem data. Because like geotem doesn't really have that much resolution to figure out that thing.
The first layer.
So that kind of thing is possible. So, well, you could put as much as you can. So if you could put SkyTem or GeoTem and NanoTem all together, in theory. You can also put different waveforms for each sounding, which might be the case in real world. So yeah, that parts are done. So yeah, it's open. So feel free to use it. I'll put some documentations if not yet, and examples.
That's great. So do you guys have any questions? I want to make sure, John or Dequan, is there stuff you guys want to bring up?
I'm okay. Yeah.
No, that's all great.
Yeah, it's good presentation. It's like it.
Yeah, anybody else? Cool. Okay, then let's maybe take a quick look at things. One thing, I'll share my screen here. One thing I would appreciate thoughts on. Can you guys see my screen?
Oh, yes. Yeah.
Yep. Okay. One thing I would appreciate thoughts on is I've been working on cleaning up notebooks to go with the casing paper we're working on. And so I'm trying to sketch out how we actually want to distribute things like this with a publication. And so this is like my sketch of the workflow, but I'd be very curious to hear what you guys think. So I've got tests running and one's failing right now because what I found is that some of my notebooks are too long to run. And so I'm using the test IPyNB, and within that you can actually list specific ones that you want to ignore. So here I know that these ones are just too big to run, so I'll just ignore those. And then what I was doing is also then, because I just had too many that are like slightly too long, I was randomly picking like 3 out of the 7 that I would run. So that hopefully, you know, if I've got a cron job on like over a period of 6 months, they'll all be tested. And so that's fine.
When you say too big, is it just a number of cells to run or the actual
No,
time
it's the computation. Yeah, the number of cells is not an issue. It's the length of the computation.
Okay.
Yeah. So there's 2 dials in there about timing. There's one that's the execute, this guy, the timeout. So this will run the notebook. So it'll time out after, that's in seconds. So it'll time out after that. So that's for a single notebook. And then there's the Travis timeout. So Travis kicks you off after 50 or so, 55 minutes. So if your sort of like integrated number of tests that you're running is too long on a single node, then they shut you down. So those are 2 things to keep in mind when you're. You can also split them up. So I have there's 2 tests that I'm running here. I have a set of appendix notebooks, and those ones are pretty light. So I will run all of them, but that's on a separate Travis node than my publication. So you can sort of see how that's set up in the Travis file. So that's testing. And then Binder is up and running and been working pretty well. The way that I've found best to interact with it is to create an environment.yaml file. And it's really easy. It's basically the same as your requirements, but you specify like what's coming in through Conda and then what your Conda dependencies are and then what your HIP dependencies are. So I found this to be a little more stable than using a requirements file, specifically because of better solvers. And we want MKL installed through Conda. So this was sort of like the best solution I've found so far. And actually, if you look in the testing, I activate this environment. So I just use this environment in my testing so that I know that like if it's working on Travis, it should also work on Binder.
Cool.
So I can show you quickly if you want to see.
So for this beta in SimPEG, you just install certain things like in this dependency?
Yeah, so in this case, well, I was installing specific branches because my stuff
okay,
for this is still on a
branches,
development branch.
Yeah.
So these are like the specific branches that I need.
Okay, yeah. I was not
Yeah.
sure of the syntax.
Yeah, so that's all that is. So then here in the testing, so what I was doing is, so here I created that environment from my environment file, then I activate it. So it's testing in the exact same environment as what will be built on Binder. So that's kind of nice.
So the pip is unnecessary then, Lindsay? Like at the line 32, or is it still required?
These are my dev requirements. So this is going to install the testing. stuff. So, because I don't need to install those like just to run it on Binder, but my dev requirements include just nose and then test.png.
Oh, right.
Those aren't necessary
I
to
see.
put on the notebook, but
I
they're
see.
necessary to test.
Gotcha. Gotcha. Oh, that's nice. That's cool.
So then, yeah, so those are all the pieces. I mean, and then naturally, like we put in a license and all of that sort of stuff. Then you can actually launch Binder or Azure. I need to make sure that this is working. I set up the link yesterday. The link works, but I didn't actually test if any of the notebooks work.
Oh, okay.
And then the last thing that I was looking at doing is using Zenodo to archive it and give a DOI. There's two options, or like two major options. So there's Zenodo and then there's Figshare. What I like about Zenodo is that every time you do a GitHub release, it just assigns a new DOI to that. So actually, if you look at SimPEG, you can see that the most recent one was the simulation version of time domain IP data. So that actually has its own individual DOI for that pull request, which is kind of cool. And then if you want to cite like the whole thing, it also gives you a DOI for whatever is the most recent version. So you can look here and see that this is where they tell you. So this is what you cite it as. And then if you want to cite all of the versions, you just replace the DOI here with this DOI.
Oh, wow. That's cool.
So that's kind of nice because then everything, like what's important about getting a DOI is that it's archived. So even if like GitHub dies one day, this code is still all archived.
Oh. Wow.
So that's why like making sure that you get a DOI is important.
So this is better than Figshare, right? I feel like.
I think they're both suitable for different things. Like I like Figshare for posters and those kinds of things. Mm-hmm. What I didn't like about Figshare necessarily was they restrict what kind of, like they relicense it when you bring it in, which is strange. Mm-hmm. And then here, like to actually just, let me see. Like all that I had to do to turn this on is like hit the on button and then you do a release and then it's just done and then it monitors. So like now that SimPEG is on there, like we don't have to do anything extra or it give you a DOI with each release.
Oh, wow.
So yeah, so that's kind of nice.
So if you need to use this same thing for like GeoSci, for example?
I think that's something that we could do, yeah, because I think it would be nice to have it archived, and then that would also make us version it, which is probably a good idea. Because right now we're not really like bumping versions when stuff has changed. And that would make it citable. So I think that would be really good.
What could be the drawback of doing that?
There isn't really, other than like we just need to make sure that we are versioning and releasing, which is something that we should be doing anyways.
Okay.
So this would just make us do it. Yeah, so that's sort of like my sketch at a workflow of how to publish notebooks with code, or like with a paper, because then you can just give the DOI, the Zenodo DOI, and say that all my code is here. So.
That's really cool. So in theory, whenever you write the paper, you make this and then cites like put that into your paper. Is that
yeah.
Is that the idea?
Yeah.
It's actually really cool.
Yeah. So then in the paper, like when we're saying all the code is available at, I mean, I give the GitHub URL, but I'll probably now also give like the citation. Yeah. So.
That's great. That's smart. So you're right now you're relying on branches that are personal.
Yeah.
Once you merge them in, you'll need to go in to change your requirements.
Yeah. Yeah. Exactly.
Yeah. It's smart to do the random test too, right? So we're saving a lot of time. Yeah. There's no point at retesting everything every time.
Yeah, especially if they're bigger notebooks, because like a lot of the ones we run are just they take too long.
Mm-hmm.
So
what we're doing for the whole stack, or no, we're still testing everything every time? Right?
For SimPEG, we test everything. Yeah, which I think is worth doing.
Yeah,
because
we're touching so many pieces. That's
yeah.
true.
But I mean, for something like this, if it's a standalone notebook.
Yeah.
So yeah, so there's examples of like this example, and then the other EM, the airborne EM one, I've done something similar. So if you guys want to take a look and copy some of that stuff, I would. Yeah, I'd be curious on your thoughts of like this style of writing. And if this makes sense, then we can actually sort of document what we're doing and put it somewhere so that it's just helpful for like setting up these SimPEG research repositories.
Okay, so if I want to create one, can I just branch off, and can I copy this and then change the name?
Yeah, you could. Yeah, so if you want to like just fork it and change the name.
Yeah.
Yeah, you can do that.
Because it's sitting in SimPEG research, but that's not the branch, is it? It's just
No, it's a repository.
It's a
So these are all like basically what the workflow I would try and do is that for every sort of new publication that you're doing or new project that you're doing, create a new repository.
Yeah, sounds good.
Yeah. So, and then like for naming conventions on these, try and use like your last name, year, and then something descriptive about it. So, yeah. Anything else you guys want to go over today? Nope. Okay.
Good.
Thanks for joining us.
Yeah, thank you guys. It's nice to talk to Soggy.
Thanks, Geek One.
Bye, guys.
Bye.
Thanks, guys.